if you have complaints about your grade, like you think that you look at the grades and you're like, wait a minute, this problem was only worth 10 points, but you took off 20. If I did that, I'm happy to fix that. Or if you have other complaints, I do have one complaint for you, and that is that some of you still don't know how to do algebra. So there were some places where it's like, come on, can't you just do some basic algebra? But there was one in particular that really got to me that I need to share with you. Where is it? I don't know where it is. Where's my notes? Just a sec. Yeah, I don't know where this. Yeah, I don't. Oh, I know. This popped up in a couple of different places. I think it was in problem 5 and some other places. But here, so let me just show you. We'll use number 5 as a springboard for this. So some of you did this sort of thing. Maybe it wasn't number 5. Maybe it was number 4. Yeah, let's use number 4 as the example. So some of you decided that you didn't like converting to polar form, which is fine, I guess. I should have made my function harder to do in rectangular form. If I had chosen differently, it would have been better, like if I'd used an annulus instead of just a disk. So there was your region, whatever. But so if you did this in polar form, it's easy because theta goes from 0 to pi over 2, and r goes from 0 to 5. You just have to remember to throw the extra r into this thing. But some of you, like I said, decided to go it with rectangular form. So let's just pretend we're going to do rectangular form. We'll get to my complaint in just a moment. So if you did rectangular form, you would need to know this function in terms of y is equal to a function of x, right? That upper function there. So let's see. This is part of this circle. X squared plus y squared is equal to 25. And so you correctly did this algebra. This is fine. It seems like you can do this. No, I'm fantasizing that you would all use r, but you didn't. And that was all good. But then here's where things started going off the rails. You would do this. Some of you put plus or minus. It really doesn't matter in this problem, so I'll leave the plus or minus off. This is still fine. Yes, this is fine. Here's what's not fine. No, that's not true. Come on. Come on, you know that here, let me just, I know some of you don't believe me that that's not true. So let me demonstrate. Let's do this. What is the square root of 25 minus 9? Let's just use that as an example. Is that equal to the square root of 25 minus the square root of 9? It is not, but just to make sure that you see this, let's actually compute this. Over here you have 16, square root of 16, which is 4. And on the right side you have 5 minus 3, which is 2, not equal. Algebra doesn't work that way. I know all beginning algebra students wished it worked this way. The same is true, by the way, if you have something like this. X squared plus y squared. Wait, let's see. Sorry. Here's another mistake. It seems like some of you made this one. And you might think, well, why? This is so basic. But yes, it is. And yet, a substantial number of you did this. So you just write this down. Sure, just square each term. No, it does not work that way. You don't believe me? Pick a couple of numbers. Try 7 plus 3. Square it. Okay, well, let's square that after the fact. So you do 10 squared, which is 100. And then let's compare that to 7 squared plus 3 squared, which is 49 plus 9, which is a far cry from 100. Not the same. So try to, these are like the stuff that you learned in 8th grade. Come on, you can do this. Just dig deep and try to do it right. So other than that, that was the only thing that I wrote down where I was irritated. The rest of the time, though, it was mainly just, you made mistakes. And so make sure you learn from your mistakes and just move on. So see me afterwards. If you think you want a sticker, like you got a 79 and you're like, I was on the cusp, I should get a sticker. get a sticker. Let's say you got a 30. You want a sticker? Take a sticker. I don't care, especially if you take Patrick. So anyway, get the stickers out of here. I have one more class. I've gotten rid of a bunch of them. Maybe I'll get rid of all of them by the end of the day. So there you go. So see me afterwards if you have complaints. The recording is going. We're moving on. So we have one more topic with multiple variables, and then we move on to vector fields. I know you're excited about vector fields, but we need one more thing. And I went back and forth as to whether or not I should do this, but I really have to. Well, I guess I don't have to, but I always feel guilty if I don't. So we're going to do it. Changes of variables. So you know U substitution, right? U substitution, that's a single variable calculus technique. So here's single variable. When you change if you change variables, it's called U substitution. So that's in single variable land. In multiple variable land, you can use U substitution if you're changing a single variable. So that's fine. But what if you want to change them both? And as an example, you already know how to do this. You change from rectangular coordinates to polar coordinates, and that's fine, right? You just know to throw an extra R in there. And that's kind of the conversion factor. U substitution, by the way, you have a similar situation. When you do U substitution, oftentimes you have to throw a conversion factor in, right? You have to throw in an extra 1/5 or 1/8 or whatever it is to correct for the fact that you're changing variables. Well, we can do this with multiple variables like with polar coordinates. And here's the sort of thing that we're going to be looking at. So I'll show you sort of an abstract version, and then I will show you a real version that we'll actually do. So abstract, this is just a, oh, come on, there it is. So this picture, let's say you're given, so ignore that for now. Let's say you're given this region, that weird looking blob, and for whatever reason, you have this, things chunked up. It makes most sense to cut this region up into these weird shapes. I know that they are not rectangles. They're weird, curved, edged shapes. So let's say that this, just for whatever reason, this makes the most sense in terms of the math, but it's really hard to conceptualize of a region that's like this. So what we're going to be looking for is a way to take this and transform it into something that is much easier to deal with. See, so you're taking all of these weird shaped rectangles and moving them and transforming them into nice, easy rectangles that are lined up with the X and Y axis. So that's sort of the goal in the abstract. Let's actually look at a real life problem that we'll actually do. Let's say I'm going to do this double integral. So the double integral of this over this weird shaped region. So here's an actual weird shape that is hard to conceal. Like, I don't know how to do that. Okay, but here's the thing about this weird shape is that if I do a little bit of math, a little bit of transformation, a little bit of substitution, I can actually take that weird shape and straighten it out so that it's a nice rectangle. Let me show you how. First off, notice that y is bigger than x and less than 3x. So let's just deal with this first. So this is going to be these two lines. So y is between x and 3x. Those are those two lines. Now take this inequality, divide everything by x, and look at what you get. 1 is less than y over x is less than 3. So one might presume that if I did this, let's let u equal y over x, then I could get this nice, easy limits like this. That's hard. It's hard to do that when you're doing a double integral. But if you have constants as your limits, that's easy. In the same way, you have these weird curves. Let's write down what the weird curves are. The weird curves, they say that y, oh, let's use a different color though. Hold on a sec. So we have y is less than 2 over x. It's got to get it right. And greater than 1 over x. So here is y equals 2 over x. Is that curve. And y is equal to 1 over x. Okay, close enough. It's doing the best I can. So that's y is between those two. If you just focus on those two hyperbolae, then you have y is between those. And check it out. We'll do the same trick, but kind of in reverse or the opposite. Instead of dividing, I'm going to multiply everything by x. And I get xy is between 0 and 2. Well, look at this. I've already got a u, so let's call this v. We'll call this one v. V is going to be xy. And then now v is between 1 and 2. So if this all works out, if I could change my variables from x and y to u and v, then my double integral ends up being really easy. I mean, it's like the best of all double integrals. The best possible situation is to have u go from 1 to 3 and v go from 1 to 2. So dv du. And then we'll have to deal with what's in here, but we'll do that. So this is kind of like what we did when we converted to polar form, but we can convert to any other set of variables. You want to describe this using 2 other letters? I don't care. You can do it. We just have to work out the correction factor. So back in polar form, the correction was to throw an extra r in. In general, though, we're going to have to do a little bit of calculus, but it's not terrible. I'll show you the calculus, and we'll do it with this. Here, in fact, I'm going to take this, because I don't have any more room. And I'm going to put it in, whoops, come on, buddy. There we go. I'll put this in Notability so that we can use it in just a minute. So let's just finish, copy, and delete. We go back to Notability, throw it down here at the bottom. There. Okay, so save this for later. So we will finish this one, but we need to do just a little bit of work. Not bad amount of work. So the work that we need to do is this correction factor. So without going into the gory details of the math, the main thing to note is that when you make a transformation like this, you're changing the shape. So we have rectangles here, or squares, and here you have this weird, it's not a parallelogram because this has a curved edge. Kind of like if you imagine the picture here, if I were to chop this up using u and v, these lines, the u would create lines that would look like rays coming out from the origin, and the v would create curved, like hyperbolae shapes going this way. So each of the little rectangles would not be a rectangle. It would actually be a piece like this. I'm exaggerating there. Something like that. However, if I could find the area of this little thing and multiply by the height, the function value in that little region, and then add up all of those, then I could easily come up with the volume, because that's what we're dealing with, is volume. So the key here, though, is that this is hard to come up with this area, but when I straighten it out using u and v, then it turns this into a rectangle, and I can find that height. Just as with the polar form, when you changed from rectangular to polar, it sort of skewed, or the formula for area got changed a little bit. We're going to do the same thing here, and the correction factor is what's called the Jacobian. So like I said, we're not going to prove this, but you could prove this, that this is the correct correction factor. I know it looks scary, but don't fret. It's not as bad as it looks. We'll do two examples. One is just the polar form example, and then we'll do the here. In fact, let's just copy this. We'll put it over on Notability. It'll be easier. So this is the correction factor that we're going to use, called the Jacobian. And essentially, what happens is you take this correction factor, slip it into your double integral, and then you're all done. You've done you've done the correction for the fact that you're changing variables. It's kind of like when you do u substitution, you do the derivative of u, and you get a du is equal to some function times dx. That's the correction factor. You have to do a little bit of manipulation. So let's go over here and actually use this. Let me just slide over here so we can see where, whoa, it's gigantic. Come down here with the rest of us. Here we go. There we go. So there it is. There's the Jacobian. I'm not happy about that. Let me make it smaller. There. I want to be able to use it, and then we'll go. So we'll use it with polar form just to show you how that works, and then I will slide over here and we'll use it with that problem. So I suppose I could just copy this. Hold on a minute. How do I do this? Copy? Why not? Let me just slide this over so that it's ready for me. Stick it down here. Okay, I know I'm making you dizzy moving it around. Okay, we're all done. Now, we need to remember our polar form. So I want to find the Jacobian for the polar change of variables. So change of variables in polar coordinates, x and y. What do x and y equal? You can jot this down while I get my attendance done, so that I can pick a rando. Which I know all of you know this because you did. Oh, some of you avoided it, didn't you? Well, we'll find out. Let's see. Random student. Tyler, what is x when you convert from polar to rectangular? Cosine. That's right. Very nice. R times cosine of theta. Beautiful. And then we need one more volunteer. You're all excited because now you know. Rachel Potts, what's y? R sine theta. Beautiful. Okay, so I should warn you about what I'm about to do. You do not need to do this for polar form because we've already done it. You know what the correction factor is. What is the correction factor? Let's see. See if you remember. I know you do. Max, what would you, if you were converting to polar coordinates, what do you stick into that integral? What's the extra thing that you throw in? An extra r. Yes. So when I get done with this, my Jacobian should equal just r. So here, let's just keep this up here in this little thought bubble. This is what I'm thinking about right now. So we've got that. Now we just have to see if it's true. Okay, so we're hoping that that's true. Let's find out. So I need to be able to compute these things. I know it's super confusing, but let's just sort this out. I will write this in terms of polar coordinates, so the functions that I have here. So instead of having u and v, I have r and theta. Whoops. I didn't mean to move everything. Let's see. Can I just move this stuff? There we go. Okay, so what I need to do is I need to compute the following items. Maybe I'll write it out first, and then we'll compute. So the Jacobian will be the partial of x with respect to r times the partial of y with respect to theta minus the partial of x with respect to theta times the partial of y with respect to r. So notice I've just copied this down. All I've done is I've changed u to r, and v has become theta. Other than that, it's just, this is the same formula. And the Jacobian is the determinant of this matrix. So that's another way to remember is, if you really need to remember, is it's the determinant of this matrix where you have x's on top, y's on bottom, the u's are on the left, the v's are on the right. And really it doesn't matter if you mix them up, as long as you're consistent. If you want to put the v's on the left and the u's on the right, fine. Same thing goes with x and y. Switch it up, I don't care. As long as you're consistent, move everything. Okay, so let us get our derivatives. So even if you didn't do well on the test, you can do well now. So we have Joshua, what is the derivative of x with respect to r? It would just be cosine theta. I should write this as a matrix just to show you what I mean by this. So here, we'll do this. Give me a sec. I will write it like this. as well, just so you can see. This is going to be the derivative of x with respect to r is cosine theta. Okay, now I need to multiply this by the derivative of y with respect to theta. And Andrew, you know the derivative of y with respect to theta, don't you? So that's the derivative of this thing with respect to theta. Leave the r alone and just do the derivative of sine of theta. Yeah, cosine of theta, correct. I think I heard something else, but I'm going to ignore that other part. So yeah, the derivative of sine is cosine. So if I was going to do this using the matrix form, I would do r cosine theta here. There we go. You know what? I need to make more room. Why do I do this to myself? Slide this back over here. Good enough. Okay, so notice that here this is the x. Here we go. There it is. And that's this one. And then this one here is this one there. Okay, let us get the derivatives of x with respect to theta now. So Madison, you know the derivative of x with respect to theta, don't you? Negative r sine theta, that's perfect. Good job. And then I need to make more room again. Just squish it down. Okay, final one is derivative of y with respect to r. And Rachel J., what is the derivative of y with respect to r? Just sine of theta. Very nice. Sine of theta. Let me stick them in this. So this would be here, sine of theta. And this is r sine, sorry, the negative. So if I were to do this in terms of the matrix, this is what it looks like. Notice that this is derivative of x with respect to r, derivative of x with respect to theta, derivative of y with respect to r, derivative of y with respect to theta, and then you do the determinant, which I don't know if have we done determinant in here of 2 by 2? It's pretty easy. There's only two diagonals. There's the down diagonal, so you multiply this, and then you multiply this, and you do this minus the up diagonal. So it's the down diagonal minus the up diagonal. That's what I have here. Let us simplify this, and you will see this amazing thing happen with this Jacobian. So we have r cosine squared theta plus r sine squared theta. Wait a minute, that's not the same thing I was thinking about. Come on, someone tell me what's going on. Oh, you got it.
Sine squared plus cosine squared is 1.
That's my favorite. It should be your favorite as well, your favorite identity, because you can take cosine and sine and eliminate them. It's like they're matter and antimatter, and they just disappear into the ether. And that equals r times 1, which is r. It was the same. Boom. So what this tells me is if I make this change of variables, I have to use this correction factor that we're calling the Jacobian after some mathematician named Jacobi. But anyway, there's the whole family. I don't know which of them this is named after, to be honest. There's a whole family of Jacobis. Okay, so let's go over and do this with the other one, the one with the hyperbolae. Here it is. This one can't be that hard. Come on, we can do this. So let's see. I need to, first of all, I need to be able to write x and y in terms of u and v. So let's see. Oh, here we go. So here's my first hurdle, is that I have v is a function of x and y, and u is a function of x and y. So I'm going to have to do a little bit of algebra. So let's do that algebra. U is y over x, and v is x times y. So I need to solve those two for x and for y. So maybe I could do this. Let's multiply both sides of the first equation by x. So I have xu is equal to y. And then I'll plug this in to the second equation, which gives me v is equal to x squared times u. Take a minute. I know algebra is hard. Those of you who aren't doing as well as you feel like you should, it's probably because of the algebra. It's not the calculus. Calculus is easy. And we should have like algebra 1, 2, 3, 4, and 5 before you get to college. That's be really helpful. It's hard though. Okay, so now we've got that. I can solve for x. So let's see, that means that x squared is v over u, which means that x is the square root of v over u. You might say, well, ho, is this going to be positive or negative? Well, check it out. All of my x's here are positive. So we're going to go with the positive square root. So positive. If our x's were negative, I'd worry about that, but I'm not. Okay, well, that gives me x. How am I going to get, oh, I could get y by taking this and shoving it into this, couldn't I? So let's see. That means that the square root, here, I'll just do this. Okay, so x is the square root of v over u times u is equal to y, and that gives me this. Y is equal to the square root of u times v. I know I skipped a step, but it's not a hard step. Take this, u is the square root of u squared. I can move it inside here. This u will cancel with one of the two u's that got moved in, and it becomes that. So there are my functions, or are my conversions. So this is the only unfortunate thing about this, is oftentimes I find that figuring out the conversion is way easier when I'm thinking in terms of taking x and y and combining them to make u and v. But to do the Jacobian, I have to reverse the process, if you will, and figure out where did x and y come from in terms of u and v. So I'll give you a minute to digest, to assimilate, and then we'll do the Jacobian. In fact, I'll get set up for the Jacobian now. Okay, so here, let me highlight. Here is my x, and here is my y. Those are the two things you're going to be using. Pick a color. Okay, so let's be very careful about this. I'm going to write these out. Partial of, okay, so give me a sec. That's not firm. Partial of x with respect to v. Partial of y with respect to u. Partial of y with respect to v. All right, go ahead and see if you can do these derivatives. Whoever gets to do the first one is going to be the one that figures it out for everybody, I'm sure. I will help you though by doing this. This is going to be v over u. 1/2 times. Oh, no, I don't even like that. Write it this way. There we go. That will probably make it a little bit easier to do your derivatives if you think in terms of these fractional exponents. So u is in the denominator, square root of u is 1/2 power, but it's in the denominator, so the negative 1/2 power. V is in the numerator, it's just v to the 1/2. These are both in the numerator, so it should be fine. All right, let's do it. We find 4 volunteers. All right, Matthew, what's the derivative of x with respect to u? You get the hardest one, but I think you're up to the task, aren't you?
Negative 1/2 u, and then some square root to 3/2.
Let's see, to the negative 3/2, very good. Yeah, the v is constant with respect to u, and so yeah, you just nothing happens with the v. So good, good work. Thank you. So now that Matthew has taken one for the team, done the first one, I think the rest of these won't be too hard. Caden, what's the derivative of x with respect to v? Oh, Caden, not here. He's probably watching the video right now saying, I know it, I know it. I'm sorry. All right, Kelsey, what about you? Do you know the derivative of x with respect to v?
It would be u to the negative 1/2 power times 1/2 v to the negative 1/2 power.
You said negative 1/2 power, right?
Yeah.
Excellent. There it is. I just wrote it in a slightly different order than what Kelsey said, just so that I could put my constant out front. There it is. Double check it. Make sure it makes sense. All right. If no one's complaining, then we're going to move on. Andrew's going to tell us the derivative of y with respect to u.
It would be 3/2.
So this is the derivative of y with respect to u.
Oh, wait.
To u. Sorry, so we're working with this right here. So the derivative of this with respect to u.
Oh, right. Yeah. So it would be 1/2.
Yes, 1/2. Good.
Times u to the 3/2.
Did you say negative 1/2?
To the negative 1/2.
That's right. Yeah. Subtract 1. That's right. Okay.
And times v at the top.
Yeah, and the v we don't mess with because it's constant with respect to u. Very nice. All right, Christopher, last one. Derivative of y with respect to v. What do you got? All right, beautiful, beautiful. So now you have two options. Now that we've suffered through all these derivatives, we can either take those four derivatives and stick them into this Jacobian matrix, or you can just use this formula to sort things out. I will use the formula because, well, the matrix is just one extra step since we've got the thing right there. So let's see if I can get this sorted. We have derivative of x with respect to u, that's negative 1/2, u to the negative 3/2, v to the 1/2, times derivative of y with respect to v, that's 1/2, u to the 1/2, v to the negative 1/2. I have it correct so far. Let me double check, because this bookkeeping is the problem, right? Once you get your derivatives, the main thing here is just keeping things straight. There's that one. And there's this one. Ooh, I should have highlighted up here too. So here's that. Okay, so far so good. Now we'll do derivative of x with respect to v, which is this, and I'm going to stick it over here. Let's see if I can do that. That was 1/2 u to the negative 1/2, v to the 1/2, negative 1/2. Oh, and there was a minus between the two. And then the final one, we're doing this weird pale orange that doesn't look all that good, but we do what we can. And that's that one. It's going to go over here, and I'm going to multiply by, what was it? Okay. Hopefully I can remember this. U to the negative 1/2, v to the 1/2. Wow, so many half powers. Well, good thing for us, a lot of these things are about to cancel. So first off, over on the first thing, the yellow and the pale green, you'll notice that the v to the 1/2 and v to the negative 1/2, basically they cancel one another because this is square root of v. This is 1 over square root of v. And these two combine using the rules of exponents. You're going to add the exponents, so this will become u to the negative 1, sorry, u to the negative 1. So that's nice. Over here, something similar happens. Let's just go ahead and combine all this stuff. I have negative 1/4 u to the negative first minus 1/4. Is it v to the, oh, wait a minute. Is it really just u to the negative 1? I guess so. So negative 1/2 u to the negative 1. I guess that's it. I'm scared now. Let me see. I did it earlier. I'm going to double check. You would think I could remember from 1 minute to the next. Did I do it? Oh, yes. Yes, I did. Oh. Hold on a sec. I get the same thing. Oh, I see. I see what happened. No, yeah, I got the same thing. Yeah, I should just not look at that. That's fine. In my notes from earlier, I have my u and my v switched, and so it changes, like, my answer is 1/2 u or v to the -1. I was like, what? But no, this is correct. This is correct. Okay, so far so good. So now here's the way that this works. We've got the Jacobian. So let's compare. Over here, back when we were doing conversions to polar coordinates, you would do your conversion, throw an extra r in. For us, for this new conversion, I'm going to do my conversion, and I'm going to throw this into the conversion. So that's what gets changed. So let's go ahead and do that conversion up here. I've got the, let's see, grab this, copy and paste. Give me a sec. Copy it. Okay, and then I'll pull this down just so I can do this again with the Jacobian in view. There it is. Okay, so let me erase some of this junk because we don't care. Ooh, it doesn't erase. That's all right. I'll just leave it there. So here's the thing, is I've got my function. Let me highlight it so you can see it. Can I highlight it in that color? Ooh, yeah. Does that show up okay? Whatever. Forest green. Forest green is what we're using today. So take a look at that forest green. I will do the double integral. And I will put du dv. I don't care what order they're in because notice that my u and my v are constant limits. So u goes from 1 to 3. V goes from 1 to 2. So far, so good. So I've got nice limits here. I need to figure out what goes in this box here. But before I do anything else, let's just stick this Jacobian in here. 1 over 2u. That's the same as what I have there. So that is the Jacobian. So let's just highlight that. This thing goes, oh, where'd it go? Where'd my u go? There. So that's that. The last step is to convert these two things. I have two options for this. Either I can use what I know that x is the square root of u over v or whatever it was, and y is the square root of u times v. You know what? We could do that, I guess. Well, I mean, the other thing I was thinking of is since this is x times y squared and v is equal to x times y, then this will just be v squared, won't it? It's not too bad, is it? So that'll be v squared. So either way you cut it, you'll end up with v squared as your, when you get done sorting out the x and the y. It's just, yeah, I just am hesitant to do this. So these two, I could have converted using those. Things would cancel. You have all these radicals. Or if you're clever, you're like, hey, wait a minute. So it's kind of like the difference between using r squared is equal to x squared plus y squared, or x equals r cosine theta, y equals r sine theta. Either way it works, but one is sometimes easier than the other. So that's it. That's it. And that will be my double integral that will do this problem. Let's do it. This one's super easy now. By the way, there's no converting back to x and y. Unlike when you do u substitution, when you do a Jacobian in a double integral, you don't have to do that. So let's see. The first one, we're doing the integral with respect to u. So let's find a volunteer. I know you're all excited about doing this one. So let's see who gets to do it. Austin, what is the antiderivative of this thing with respect to u? Okay, so negative ln of u, you said? Or did you want to put a 2u in there? Yeah, let's not put the 2 in there. Here, just to make it more clear, let's do it like this, just to simplify things. You could do that. I'm not opposed to it, but I think it'll be easier if we separate the 1/2. That way we won't have to worry about additional substitutions. So it's negative, let's just make it negative 1/2. Is that all right? And then what happens to that v squared? Yeah, nothing. Yeah, right. Yeah, you're like, I'm not going to say anything because there's nothing, right? Okay, very nice. So this u goes from 1 to 3. This is the inner integral, and then the outer integral is this one. Okay, so I'll pause and make sure that that makes sense. By the way, some of you are thinking, why isn't that the absolute value of u? Okay, I'll make it the absolute value of u, but because we're dealing with only positive numbers in this integral, I could just leave off the absolute value, but I guess technically I should do it like that. All right, looking good. Next, we're going to actually plug in our limits. So this will equal the integral from 1 to 2 of negative 1/2 Ln of 3 minus Ln of 1 times v squared. I know I kind of did this in a weird way, but if you plug in the two limits, you can factor things out. So you can just plug it in right there. And we all know the natural log of 1, don't we? What's the natural log of 1? It's 0, yeah. And if you didn't know, you have calculators, you can use them. You know, might as well simplify this even further. So almost done. 1 to 2 of negative 1/2 Ln of 3 times v squared dv. All right, one more antiderivative that Matthew's going to do for us. Matthew, what is the antiderivative of v squared? Oh, it's amazing, isn't it? So this is going to be, let's put this 1/2 Ln of 3, and then you've got v to the third over v, which I'll write like this. And then we're going to plug in v equals 1 and v equals 2. So all that's left is plugging in our numbers. It can't be that hard, could it? So let's see, plug in v equals 2, and I get 8 thirds, 8 sixths Ln of 3. And then, oh, that's negative. And then I'll plus 1/6 Ln of 3. And this all boils down to negative 7/6, which doesn't feel right to me. Let me look at my notes. I feel like there's something wrong. Give me a sec. Let me look at my notes here. There, that looks, oh, yeah, I got 7/6 Ln of 3. It shouldn't be negative. So what is wrong? There must be a mistake. I don't want to go hunt it up. There's a plus and a minus. There's a negative mistake somewhere. So probably in the computation of the Jacobian, probably this should be positive 1/2 u. So that's my guess, is that there's a mistake here. I'm going to write it down, 1/2 u to the negative 1, question mark. So that's probably where the mistake was, is somewhere up here. I will double check later. I don't want to do it now. Probably there's a negative out of place somewhere. Shouldn't one of these be negative? Hold on. Maybe I can find it. That should be negative. This one's already negative. Is that the only negative? Huh. Jacobian. Jacobian. I wonder if I'm mistaken with my formula. I'm wondering if I should put absolute value symbols around there. I'll double check though. I think that might be the problem because it's the negative. The negative is the problem. It shouldn't be negative. It should be positive. But we're doing good, other than the fact that this is negative. The correct answer I have from my notes is 7/6 Ln of 3. All right, let me see if there's anything else that we can do for fun. Blah, blah, blah. Oh, yeah, here. We'll go back to PowerPoint. That'll be fun. So we'll do PowerPoint just for a minute, and then we'll take a look at homework. So changes of variable suggestions. So if you have a problem where you're like, I think I should change variables, you should look for ways to fix the boundaries. Like if the boundaries are nasty curves, is there a way that we can maybe make a substitution to take those nasty curves and turn that into a nice rectangle, like we did in this last one? Then we're going to first write u and v as a function of x and y, and then you have to actually do a solution solving for the x and y as functions of u and v. I have one more example that we could do, but I need to just show you something about the homework so that you aren't too frightened of this. So let's see, where is it? Is it here? Here it is. So here's the homework. I forget which problems that you're doing, but here's the deal, is in the homework, they're really kind to you, and they say, find the Jacobian, and they've already got x and y in terms of u and v. So you would do the partial with respect to u, the partial with respect to v. Same thing here, combine them using that Jacobian formula. It's pretty straightforward, pretty easy. And then when you're doing the double integrals, you have, where is it? I don't think I made you do those. I don't think I made you, where is it? Oh, here it is. Here it is. So I skipped these. These are the ones where you have to be a little bit more creative, where you have to come up with your own conversions. So I skipped that. So, and you know, because that's hard. I don't want to say that I don't have faith in you, but it is hard. And so I wanted to just practice the easy stuff for now. So here with these problems, when you get down to this section, you're going to do the double integral, and they tell you what your conversions are. So they give you the conversions, so you can easily go in here and say, okay, x is 2u, y is 3v. So you're going to change this to 4u squared, I guess. And there is no v up here. And then you're going to do this with this ellipse, but if you change x to 2u, this becomes 36u squared, and this becomes 36v squared. So it takes an ellipse and turns it into a circle. So that makes that easier because it's circular instead of elliptical. Same thing goes up here with these. I forget which ones you have to do, but you're gonna, you know, take the conversion that they give you. You'll probably, with each one of these, they tell you a region. You'll want to draw the region so that you can see what it looks like. It'll be some weird triangle or some parallelogram, and then apply this to each of the corners. Ooh, well, you'll have to do some solving, some algebra. So, if, for example, here, x is -1, y is 3, what are u and v? Figure out where that maps and so forth. But then you'll be able to set this up, and then you can make your Jacobian. So that's what that looks like. In fact, let's see, it's 10 minutes to go. So let me take a peek at the homework, and we'll just start one of them because I sense, I think that this is going to be a problem possibly. So just give me a sec, multi. So we'll do the first one that we have on the list that is a hard one. Just a sec. So assignment list, because we got 10 minutes. Here it is. Oh, I don't know what page number this is. It's section 15.9, because I was looking at my online version of the book, and I don't know what page, but you can figure it out. So let's take a look at number, let's see, 15, 16, and 19. Let's start 15, just to show you how this is done. So take a look at that. It gives you this triangular region. So step one, so we'll step our way through this as much as we can. I'll do the hard part for you, though. I think that getting the Jacobian is going to be easy. So let's see, put this down here somewhere. There it is. Okay, so step one is to draw the picture. Let us draw this picture of the region. The vertices are 0, 0, over 2 and up 1, which is right about here. Let's just mark this off, label the graph, and over 1 and up 2. So that's this. So you have this unfortunately, weird region here. It's kind of a weird triangle that's rotated. It would be nice if this was aligned with one of the axes, but it is not. So they suggest these conversions. So what I need to do, this is x and y. I need to do the transformation to get to u and v. So the way I'm going to do this is I will take each of these vertices, plug them into the conversion. So x is equal to 0, y is equal to 0, and then figure out what I need u and v to be. So it looks to me like if I solve these two equations with two unknowns, let's see, this would be u is -2v, that's this one, and then plug that into the first equation, because I know you guys like substitution better than elimination, even though elimination is far superior. Sorry, that should be a v. So plug this into the first equation, Let me highlight so you know what I just did. I've taken this and I've plugged it in here for u. And that gives me negative 3v is equal to 0, or v equals 0, u equals 0. So that's this point right here. That's one of the 3 points, though. Let's do the next two. So with 2, 1, 2 is equal to 2u plus v. Notice I'm using this equation. Whoops. I'm using the equation up on the upper left. X is equal to 2u plus v. Y is 1. So I'm doing this one now. 1 is equal to u plus 2v. So let's solve this. Oh, I'm so tempted. Let's use elimination. I can't handle substitution. I'll multiply this. Here's a second. I'll multiply this bottom one by 2. So 2 is equal to 2u plus 4v. And 2 is equal to 2u plus v. And I will subtract the bottom one from the top one. And I get 0 is equal to 3v. So v equals 0, sorry. V is equal to 0. And then plug this back into one of the original equations, and you get u is equal to 1. So v equals 0, u equals 1 is the second point. So this will be 1 here. So apparently that's this point. So let's see, this point here ends up right here. This point here ended up right there, interestingly. And then the final point is 1, 2. So give me a minute, I'll do the algebra for you. You'll have to do the algebra on the other problems. So let's see, this is x is 1, y is 2. Okay, so x is 1, y is 2. I will let's double the top equation. So if I multiply this times 2, I get 2 is equal to 3u plus 2v. 2 is equal to u plus 2v. So this will be times 2 times 2. And this is, you just write it. So you can use substitution if you don't like my elimination method. It's not mine, it's the way most people do algebra. U equals 0. And so now we'll plug this back into one of these, and you find that v equals 1. Okay, so that's this point right here. And that's the third point. Boom, boom, and that's 1 over. So you can get your own Jacobian, but notice that the region it kind of straightens out spreads out the triangle so that it's nice and easy. So when I set this up, here's how it's going to look. You just have to come up with the Jacobian. So I'm going to use a vertical rectangle. So u goes from 0 to u equals 1. V goes from 0 to v equals 1 minus u. That's this line, v equals 1 minus u. And then you're going to have to come up with your Jacobian. You're also going to have to convert the function. So I guess I will say times the function, but you'll have to convert it to u and v. And then dv, du. And you're all set. So yeah, you come up with your own Jacobian, you can do that. It's not hard. But so that you'll have to do 2 more times because there's 2 more problems like this that you have to do the conversion. But they give you, isn't it nice? They give you the hints as to what your conversion will be. So hopefully it won't be too bad for tomorrow. So stick around. Remember, I have some additional stickers. If you don't like Patrick as much as I don't like Patrick, I have some more of these, and you can trade. Or if you didn't do as well, but you want a Patrick, take a Patrick. I'm happy to get rid of them. So there you go. I'm going to stop the recording in case you want to come and complain about your test.